key management. So each individual they have to only maintain. Two key. Okay. One is private key and one is public key. Okay. So public key will be known to everyone, and private key I keep with myself. If anybody wants to send a message to me, that message he can encrypt with my public key, and give it to me, and with my private key, I can decrypt that message. With my private key, I decrypt the messaging. So I hope everybody knows about this. So the famous example of this is RSA, Diffie-Hellman, LGML. So general strategy is a public key is used to encrypt a message, and that can be decrypted only by corresponding private key. So public key, private key comes in pair. If any message I am encrypting with my private key, okay, okay, and at the receiver end, if you can decrypt that message with my public key, that is for sure that it has been encrypted by the private key of the owner. So private key and public key comes in pair. So the message which I encrypt with private key at the receiver end, if that message can be decrypted by my public key, then I am the one who has sent that message. Okay, I have to own that message. So Bob uses Alice public key to encrypt a message. Only Alice can decrypt the message. Similarly, if Alice wants to talk to Bob, then Alice can encrypt with public key of Bob, and they can communicate with each other. So it looks like this way, the same encryption algorithm and decryption algorithm. Here keys are different, and they comes in pair. This comes in pair. So what I do, here I don't have to maintain n to n. So if there are n people in a system, I don't have to maintain n-1 key with everyone. I'm telling individual user don't have to maintain, just like symmetric key. Individual user don't have to maintain n-1 key. Only I maintain one public key. I can maintain one public key, I give to everyone, and with that public key, if anyone wants to communicate, he can encrypt and give it to me. I can decrypt that message with my private key. So another important concept that is required to understand, to appreciate the blockchain is hashing. So what is hashing? Hashing is like we have a message, and there's a hashing is a function that takes arbitrary length message and gives fixed length output. This is also called message digest. So every time if I give Rakesh Tripathi my name, it will give the same digest. It is just like a footprint kind of thing. Okay. If I give Rakesh Tripathi to this one, then I will get the fixed length some digest. If it is 128-bit digest, then I get 128-bit. If it is 256-bit output hash function, then so for example, SHA-258, SHA-128, SHA-256, depending upon the algorithm which we are using. I can use SHA, I can use MD5, MD4, whatever I can use it. So these are the functions that takes variable length message and gives fixed length output. It is also called message digest, or it is also called digital footprint of this message. So if you see, the message is of variable length, and the output is of fixed length. So theoretically, if you see, many more message will map to the same hash function. So here, if you have a message can be of 1000 bit, and this is say 128 bit. So you will find that 2 to the power 1000 divided by 2 to the power 128 message will map to the same hash value. Am I right? This many message will map to the same if they are equally probable. If each of the message 2 to the power 1000 bit is the search space of this one, and 2 to the power 128 is the output space of this one. So all input space has to be mapped to some of the output space. And if you assume that each of the input message is equally likely to go to any of the hash output value, then 2 to the power 1000 by 2 to the power 128, it will be 2 to the power something 800 862 or 872. 2 to the power 872. Am I right? 2 to the power 872 message will be mapping to one hash value. You must be thinking it is very easy to find hash collision, but no, because search space itself is very large. We'll see that. So hash property, what is the property of cryptographic hash function? Cryptographic hash function property is, if I give any variable length message X, I should get, I am audible to all of you?
Yes, sir.
Okay. So so these are the property of cryptographic hash function. These are the property of, let me write, cryptographic hash function, not the hash function. Cryptographic hash function. The hashing you must have studied in your somewhere you have seen. Cryptographic hash function. These are the property. Property first is it is very easy for a given message X. For a given message X, it is very easy to find h of X. And once I know h of X, pre-image it is very difficult. If I know h of X, 128-bit digest, what message gives me this digest? Very difficult to find. So it is pre-image resistant. Pre-image resistant. Collision. If I can find X and X prime such that both give the same hash value, then we say collision. X and X dash are the collision. We found one collision. So second pre-image resistant is the second property. If this is the first property, this is the first property. This is the second property. Pre-image resistant says that if for a given X I get HX, it is very difficult to find another Y that gives same HX. It is called second pre-image resistant. You got any point? If this is given, it is very difficult to find this. Very difficult to find this. It is called second pre-image resistant. If this is given to you, it is very difficult to find what two X and Y give the same hash. Or it is very difficult to find two value X and Y that gives same hash. It's called hash collision. So what you expect from a hashing function is it should be very difficult to find two value that gives the same hash. So this is called avalanche effect. So if you see fox, if you give to a hash function, you get something like this way. If you get the red fox jumps over the blue dog, this is the hash function I get. It's a fixed length hash output and for the variable length input. Now if I change OV to OU, you see it has changed a lot. Almost it is completely different. This is why it is very difficult to find pattern. Very difficult from the output. It is very difficult to guess what two input will give the same digest or what input will give this digest. Okay, if I change OU to OEV, then you see it has changed entirely. Okay. Now, why this works actually? See, arbitrary length message is mapped to fixed length message. Means many message will be mapped to the same hash value. So if I say, let's for our assumption, 1000 bit is the message space, then how many message I can have? 2 to the power 1000 different message I have. So 1000 bit message means I can have a message of length 1000 bit. So how many unique message I can have? 2 to the power 1000. 2 to the power 1000. Am I right? Now, if my hash function, I have told you that it will take a variable length message. It will be variable length message, and I get a fixed length output, say 128-bit output. I'm talking about this scenario. 1000-bit input message, okay, and I am having 128-bit output. Now, what will happen? 2 to the power 128 possible hash value I have, and 2 to the power 1000 different message I have. So how many message will be matched to same hash value? 2 to the power 1000 by 2 to the power 128, it will be 2 to the power 872. Am I right? 2 to the power 872 message will be going to same hash. So theoretically it looks, oh, so many value message will be going to same hash value. But if you have to search for two value, it is very hard. See, if you have to search for two value, so if I give n bit hash output, on average you need to find 2 to the power n by 2 trial you have to do. Means say you got a hash value for mine, Rakesh. You give to a hash function and you got some digest. The output is called digest. Now what other message will give you same digest? You have to try 2 to the power n by 2 trials on average, if n is the output bit value. And this 2 to the power n by 2, if it is 62-bit hash, it will be 2 to the power 32. And if it is 128-bit hash, that is 2 to the power 60. You must be knowing on average you go half. You do half. So 2 to the power 64. And 2 to the power 32 is not fair. This is feasible these days. 64 is infeasible. But these days we don't go for 128-bit hash. These days you see the SHA which bank uses, it is 512. 512-bit hash. 512-bit matlab you have to do 2 to the power 256 different try. It is impossible. What other value will give you? That is why this hash works. Even if theoretically you will see that many messages are going to the same hash value, this hashing works. Okay. So SHA is an example of a hashing algorithm. Now we'll see digital signature. Now what is digital signature? Digital signature is used to verify the correctness of a So I got a message. How do I know that this message is correct? How do I know that this message is correct? By digital signature. Okay. So digital signature, we'll see how it works. So digital signature, it came from correct person. You have to check it. You have to also be sure that the message which is sent and the signature which is there down, this has not been modified. This message and signature has not been modified to M prime and signature prime. It should be intact. Message should not have been tampered. And it is also used to prove that whoever has created the signature, he is having corresponding private key corresponding to the public key with which the signature was created. I will tell you what it is, what do I mean by this. So what do you expect from a signature? So only you can sign. The signature you should have, only you can put your signature. So I can put my signature, nobody else should be able to put it. So you should be able to verify, okay, this is the signature of Rakesh Tripathi. So everybody should be able to verify it, but nobody should be able to forge it. Okay. So for paper, for document, it is easy. I'm putting my signature, nobody can cut and paste it. But for digital document, if I have a digital signature, this is the message, and I'm putting a digital signature D below M, then you cut it, you cut this D from this message and you put this signature with M prime. So you can forge it. So what we do, digital signature basically ties a signature with the document itself. And how it is tied? So digital signature consists of 3 algorithms. So I'm a bit fast because I know that you are knowing this cryptographic primitive. Just for the sake of completeness, I'm supposed to do this, then only you'll be able to appreciate the blockchain concept. So digital signature basically consists of 3 algorithms. First one is SK and the second one is PK. So these two, you generate a pair of key. I've told you it is based on public key cryptography, SK and PK. So with SK, this is a secret key. You have to keep this key secret with yourself, and you are signing. You sign a message with this secret key. You sign a message with this secret key, and it gets, and whatever signature you are putting, it gets verified by your public key. So it is your responsibility to keep your private key with yourself secret. And how do I sign? So there's a sign is a function that takes message M and my private key SK, and it returns sign. And then I will be sending this message and sign. I will be sending this message MSG and sign to receiver. Now receiver knows my public key. Receiver knows my public key. I'm sending message to him. I'm sending sign to him. And this verifier is a function. If it is true, then signature is valid. If it is false, then signature is not valid. How it works? Let us see. So what I do, basically I create a hash of a message, and then I encrypt the hash with my private key, okay, and send along with message to the receiver side. Receiver side again compute hash onto a message, and it computes and it checks the computed hash with my decrypted hash. So what I do, so Alice has to send a message to Bob and he wants to sign it. Then what he does, on a message M, he runs the hashing algorithm and he finds a hash. Okay, this hash, it encrypts with his private key A. So A is the private key of Alice. 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 Now, this hash, encrypted hash, I send along with message. So this is the message. This is the message. This is the encrypted hash. This is the encrypted hash of message M, or you can call it P, message P. Okay, this is P, make it P, packet. So this packet I send along with encrypted hash. Okay, along with encrypted hash. Now Bob, what he will do, he will pass on this message with the hash. He will get this hash H of P, and then whatever encrypted hash I got, I decrypt with A. A is the private, A is the public key of, so A is the public key of Alice. So public key of Alice is A. Public key of Alice is A, and private key is small a. Now he can, and he checks if these two are same, means the hash I can put on this message M, and the decrypted, the hash which was encrypted by his private key, and I'm decrypting with his public key, and I know that private key, public key work in pair, complementary to each other, means a message I encrypt with private key, then I can decrypt with corresponding public key only. And if I encrypt with public key, then I can decrypt with corresponding private key itself. So this is the way actually this signature works. This is the entire flow chart. So importance of digital signature is it helps to tell that message is coming authentically. Means I am sure if I am able to decrypt the hash with your public key, so it must have been encrypted by your private key. So you are the person who is having this corresponding private key corresponding to the public key with which I have decrypted. And it is also used for data integrity because I am encrypting a hash of the message. So once you change a message, then it won't match. Your signature won't match in the end. And non-repudiation. Non-repudiation is a phenomena where the sender cannot deny later on that I have not sent this message to you. You have sent this message to me because I was able to decrypt the hash with your public key. And how I'm sure with your public key? Because the decrypted hash, whatever value I get, and the message you sent hash, those hash are same. It means that you have encrypted with corresponding private key of this public key with which I have decrypted. So you are the owner of that private key and you have encrypted that. So non-repudiation, nobody can deny that I have not sent. Some more terminology, non-repudiation, I've already told you that a sender should not be able to deny sender or receiver that I have not got the message. And replay attack is the same transmission, I am again repeating it or I'm delaying it. It's called replay attack. Now we'll start with blockchain introduction. So what is blockchain? So blockchain is nothing but a software. It's a protocol that gives you a framework where the asset could be anything. It could be money. It could be your land record. It could be student degree. It could be anything, any object of value. Any object of value, I can store that value in blockchain. So blockchain gives you a framework where I can store it. And once I've stored it, it cannot be modified. And then I can also ensure that when the value is changing hand, when asset is changing hand, I can record those transactions and I can always claim who is the owner of this record currently. So blockchain gives you a framework where I can store my data. That data will be immutable, and whatever data I am writing, it will be visible to, transparently visible to all stakeholders. And whenever that object or asset is changing hand, that will be recorded, and I can know that who did what. I can do entire, trace. I can trace the land record, who sent whom, and in what order, in what chain. So it is applicable everywhere. We'll see that where it is applicable. So if you know the TCP/IP protocol stack, then there is internet. This is the infrastructure, networking infrastructure, and you have application layer protocol, and then you have application. The way email uses SMTP, phone call, Skype uses voice over IP or multimedia RTP protocol. Bitcoin is an application that runs on top of the blockchain framework. Okay, blockchain framework. So blockchain is again a platform. It's a software. Okay, and there are protocol in which different party exchange message and you achieve something. So you can develop a distributed application on top of this blockchain. And what are those applications? We'll see that. So it started with the blockchain idea started with your Bitcoin in 2009. The Bitcoin came, and the first and then Satoshi, who gave this idea of Bitcoin, he disappeared in 2010. So first code of Bitcoin client was rolled out in 2010 January or 2009 December, somewhere around that. And then we got Ethereum, Hyperledger in 2015. There again one blockchain platform where you can write smart contract, and on top of that you can write different business application. And then there are demand for blockchain increases in 2018. Then Walmart is using. There is Estonia, a country, they have shifted entire of their healthcare record onto blockchain. So now it started with the blockchain started with cryptocurrency, but now people are finding way out to use blockchain in other application area, maybe healthcare, maybe industrial automation, smart cities. People are trying to use it. What is blockchain? So blockchain, if you see, technically it's a linked list. Blockchain is a list of block. So it is also called a linked list. And linked list, the only difference is it's rather than you have a pointer to a previous node, you have a pointer to previous node of that hash value. We'll see what is that. What do I mean by that? That linked list is replicated. The linked list, the blockchain chain of block is replicated across multiple sites, and it is also called distributed ledger technology. Okay. And in blockchain, the data which you are writing, so this block will be cryptographically linked with this block. We'll see how it is linked. And there's a notion of consensus. Who will write into this block? Okay. that will be decided by consensus mechanism. So consensus means, say 4 or 5 of you friend, you agree on lunch where we'll be going, on dinner we'll be going. So consensus is a mechanism by which different party reaches to an agreement on any value, any state value. Okay. And so these are the property of a blockchain, that they are replicated, they are based on distributed ledger technology, and you write onto that ledger, writing onto the ledger is based on consensus, and all blocks are cryptographically linked, and this cryptography assures integrity of data, immutability and data. We'll see how these things are possible. And it is used to implement an immutable ledger, means if anything, if you have implemented blockchain, then once you have written, nobody else can change it. It is immutable. And if anybody changes it, then it is a temper evident law. Temper evident. I will find someone has changed that law. And third is, it is a platform to create and transact cryptocurrency, or it's a platform to enable a transaction of any asset. Asset could be cryptocurrency. Asset could be your, as I told you, any object of value. Okay. So blockchain, the idea of blockchain is, technology is new, but the component that it is using is based on ledger, cryptography, wallet, asset, and there is a notion of consensus, there is a notion of immutability. So at the core of blockchain is a ledger. At the core of blockchain is a ledger. And what do we mean by ledger? So ledger, you must be knowing the old khata book. You have a banking transaction, you know. So I debit account, credit account, and amount. So this is one ledger. This is one ledger. So ledger is like, you have a book where every row will have a record certain transaction. So Ram has given some money to Shyam this much, okay, and then you record a transaction. So it's nothing but a database. It could be Excel spreadsheet. It could be any you know, this one. Now, what is blockchain? Blockchain is not a ledger. It's a, so there's a notion of distributed system. Then there's a notion of distributed ledger, and there's a notion of blockchain. So distributed system, you all know that distributed system consists of computing node. They are geographically distributed. They work together towards a common objective. Distributed ledger is the notion of that you have a database that is distributed all across multiple sites. So you have a database, and you replicate that database across multiple sites. It's a distributed ledger. And the blockchain is a bit different. It is a type of a data ledger technology. It's a type of data ledger technology where, yes, the ledger is distributed across multiple sites or shared across multiple sites, but it is arranged in block. So each page of transaction will be linked together with next page, and they are cryptographically linked. These are cryptographically linked. But distributed ledger, they don't talk about any cryptographically linked, or they will be organized in a form of block. It is silent. So blockchain is a bit different. They are more secure, they are more immutable, and all blocks are cryptographically linked. So it has more feature than typical distributed ledger, concept. Blockchain, it's a decentralized peer-to-peer architecture. Okay, the simple definition of blockchain without any technical words. Blockchain is a decentralized. So the difference between decentralized and centralized is, centralized SBI. SBI is the one who owns the entire database. He is the one who will write everything. Okay, he has taken this money and given to him. He is having this much balance. So this is the credit card. Everything is in the hand of a bank. Bank writes, bank manages. Blockchain is decentralized. Means you have a distributed ledger. So database is distributed across multiple sites. Who will write into the database? It is not fixed. Anybody can write it. That is why it is decentralized. There is no central authority who is doing that. More than one party are. So in public blockchain, anyone can write. In private blockchain, I will tell you what is public and private. Private, there are set of designated node only who can write. There is no central body who is writing. So member in the network record the digital transaction in shared ledger, okay, and all of them will have the same copy. What do I mean by this? So what problem? So the first thing that blockchain does, okay, simplest is, earlier we had a common ledger, SBI. Everybody was talking to SBI. Ledger was in the hand of SBI. He is the one who is managing everything. With blockchain, what happened? This ledger has shifted to, everybody is having that copy of this one, okay. Whenever any transaction happens, that transaction is flooded, appears on all, if this is down, let it be down. Whoever is up, they will be recording this transaction up. Once he's up, he will talk to nearby node and say, you tell me the latest, ledger status, and then he will copy the entire ledger from him, and he'll be also up to date. So this is the idea of blockchain. The ledger you shift to across multiple sites. So this is also a distributed ledger technology. That ledger is distributed, shared across all sites. And whenever any transaction happens from C to F, directly it is happening. Earlier, if C to F has to happen, he has to say, take note of this transaction. Then he was executing all transaction in this ledger and notifying F was getting, okay, yes, transaction is, my account is up to date. Now, here in blockchain, we don't have that. You have a ledger distributed across all sites. We have a ledger which is distributed across all sites. And whatever transaction is happening, it will be recorded on all replica. Okay. It's a peer-to-peer network based, means like there is no client server kind of thing. There is no central party we are going. All are of same capability. So Bitcoin works on peer-to-peer network framework. Okay. So distributed ledger and peer-to-peer. So this definition, it's a decentralized peer-to-peer architecture is like this. It is decentralized. If C is transferring money to F, then C will tell everyone, see, I am transferring this transaction, this money to F, to everyone. Okay, to everyone he will broadcast. So everybody know, yes, C is transferring this. And so everybody will verify that, yes, this is the valid transaction and update their ledger. And how they verify, we'll see. So it looks like this way. There's no central server. There's no central server. Everybody will have the same copy of this ledger, same copy of ledger. So everyone is, and the ledger is traceable. So this is the block 0. So it is holding block 0 data and hash of this. And at this timestamp, this data was added to the ledger, and previous hash was nothing, so 0. Now this is block 1. This is block 2. So there's a typo. Block 0 it should be block 1, block 2, index 0, index 1, index 2. So timestamp of this is, again, you change it, make it 35, make it 45. So at this timestamp, this block was created. So I have copied, I have not changed this one. Okay. So this hash value I am changing. So what it is doing, for this block, whatever is the hash, I put previous here. So this is how it is changed. It is chained together, cryptographically linked. So how? So whatever transaction I am having, transaction I write here, and hash of this entire block, hash I write here, previous hash is 0. Now the next block which I am adding to the chain, this is the block 1 data. There's a typo, it should not be 0, it should be 1. Block 1 data, now I compute a hash of this data, I get this hash, and previous hash, it is binded to this. So whatever is the previous block hash, I write here. So this is why it is called cryptographically linked. So if someone changes this data, this hash will change. If this hash will change, then he has to change this hash. If this hash changes, then what will happen? This entire hash. So this hash is computed based on entire this block. This hash is entire block data, timestamp, index, and previous hash, everything. Okay. So this is why it is cryptographically linked. We'll see what is tamper-proof. So blockchain, the way we have a pages, we have a block. So whatever transaction you write in one page, you can write in a block. Next page you write in next block, and they are connected cryptographically. They are connected cryptographically by this hash pointer. We'll see what is this hash pointer. Technically, what is needed, we'll do that. And structure, so this is a block 1. So previous hash is 0, and the block hash, you compute hash on everything. So this block is consist of all transaction, record 1, 2, 3 for all transaction, and there's a nonce. Don't worry about these things. So I compute hash on everything, okay, including previous hash, I get this hash, okay. Once the new block is added to blockchain, all transaction are written, and I take a nonce and I compute hash on, I put previous hash here, 0501, I compute hash on this, nonce, everything, I get this. Now the next block, if I get next transaction, if anyone is doing, it will be again broadcasted to everyone, and then one of them will cast a block out of those pool of transaction, and it will be appended to chain of block. And how it will be appended? The previous block hash will be written here. This is a new block hash. New block hash is computed based on this hash, this nonce, and this all transaction. I get this hash. Okay. So this is the way actually it is cryptographically linked. Okay. The feature of blockchain is the public distributed ledger which records transaction and provide decentralized transaction data management. It operates on peer-to-peer network. A transaction recorded in the ledger can never be changed. An identity can be hidden. We'll see how. and the system is secure as there is no central point of failure. Now see, if this has failed, no problem. Transaction can, if you want to initiate a transaction, he will initiate a transaction, send that transaction to everyone will add, and it can proceed. More than 51% of the node should be up. More than 51% of the node should be up. We'll see that. Oh, Byzantine fault tolerant concept is there. So 2/3 should be there up, not 51, 2/3. So let us not indulge into those part. So there's no central authority, there's improved tolerance to failure. Okay, so blockchain is distributed. You know why it is distributed? That a ledger, I have all transaction which is occurring, I write into block, and block by block transaction will be appended into block, and this block will be linked cryptographically. And how? So for one block, whatever transaction is there, I have a data field called previous hash. So previous hash will be 0 for the genesis block, for the first block. Once the next block, all transaction which is flooded is added. How it is added? It is added, it will keep the previous block hash, again it will compute hash, and that is the hash of the block. And this blockchain is distributed across multiple sites. So it is distributed, it is decentralized because anybody can write to the ledger, anybody can add block to the blockchain. Okay, it is not fixed. And who decides, who gets chance, we'll see that. Immutable, we'll see how it is immutable. It is transparent. How it is transparent? Because earlier MIS, our SBI transaction database is with whom? With SBI. Now SBI is the custodian of my data. SBI can do anything. Now how the transparency will come? If the SBI transaction is available to everyone, then it is more transparent. And there is disintermediate, means there is no need of trusted third party required. Directly if A want to send to B, then A will flood their transaction to everyone. Okay, so everybody will have the transaction pool, and then one of them will be asked to add block to the blockchain, and he will send that block to everyone. We'll see that. We'll see. So what happens, what I'm telling? If there's any transaction happening, say if any transaction is happening, if this node, which was a part of a, so who is this? So this is node. This is a node. If he want to initiate a transaction, so they are having this ledger. Ledger is there like this way. So everybody is having this two block. Everybody is having two block. Let us say the state of the system is like that way. Okay. So if he is starting any transaction, if this node is involved in transaction, sending money from A to say M, then he will say, okay, I'm transferring $2 from A to M. Now this transaction will be flooded to all the nodes, okay, all the nodes. Likewise, if this node is initiating any transaction, it will flood it to all of the nodes. Now once the so everybody will have a transaction pool. Whatever happened in last 1 minute, everybody will have a transaction pool which keep record of what transaction happened in last say few minutes. Now one of them will cast a block out of this. For example, this guy will cast a block out of, randomly a guy will be chosen out of these fellow. Out of these node, randomly one node will be chosen to add a block to the, what is block? Block is a collection of all transactions. So whatever transaction happened, say 100 transaction happened, I pick up say top 80 or 80 which I like, and I cast a block and I add this block to the blockchain, and I tell everyone, see, this is the block I'm adding. This is the block I'm adding. So everybody will add that block to their chain. And everybody will verify whatever transaction he has added, that is correct. So everybody has to verify it. This is called consensus. Consensus means everybody has to agree onto the state of the blockchain. Okay, what transaction will be added into block and in what order? So they have to agree. So diagrammatically, if you see, so this is the blockchain network. If this node starts a transaction, it will be flooded across all network. Everybody will have a transaction. So everybody will have all transaction which happened. Okay, so everybody will have the transaction pool. Now one of them will be chosen randomly. What is that random? We'll see. One of them will be chosen randomly, and he will add that block. He will cast a block out of those memory pool of transaction. This is called memory pool of transaction. Memory pool of transaction. So everybody will have this memory pool. one of them will randomly be chosen, and he will cast a block out of this. So he will choose set of transaction he will put here, and he will add this block to the blockchain. He will add this block to the blockchain and tell everyone, everybody will have blockchain up to this point. And out of them, one of them will be chosen randomly to add block to the blockchain. This is called consensus finality. Okay. So this is called so this is the consensus node. So all node who are participating. So this node, everybody will add this block to the blockchain, because once he has casted this block, he will tell everybody, see, you add this block to our already existing blockchain. Everybody will verify the transaction which he is adding into the block. If all are correct, okay, the correct owner is spending the money, then okay, it is fine. Okay. So this is the verifiability. So all minor node, they verify all transaction. These all transactions are correct, and they participate in consensus. Consensus means who will be permitted, who will be given chance to write block to the blockchain. This is what consensus algorithm says. So this is the set of node everybody is having. Now who will be adding a fourth block? Okay, who will be adding fourth block? It is chosen randomly. It is chosen randomly. Chosen randomly or probabilistically. Randomly. And we will discuss one such is proof of work, proof of stake, proof of, there are many. Since this is not a blockchain course, so I will be just giving a brief idea. Okay. Now, what are the components of a blockchain? The component of the blockchain is there are nodes, there are asset. Asset is what is changing hand. You want to keep track of. Transaction is what the smallest record of the building block of blocks, and transaction is what that give information about asset. Give info about asset. Info about asset. And there are block, and there's a wallet with which a transaction is initiated from our wallet. And there are miners. Miners are the node who participate in the consensus process, who will be given chance to add block to the blockchain. And there's notion of smart contract, and we'll see that. So component of the blockchain is a ledger. There's a ledger. So all nodes, they have a ledger, and this ledger is immutable. And we use cryptography. We use cryptography to achieve that immutability and tamper evident lock. How we get that? Then we have peer-to-peer network. Then their asset, which I want to protect. I want to keep track of, okay, this asset, how this asset changed hand. Okay, this land record, first this land was with me, then it was purchased by A, then it was purchased by B. All those transactions I can record in blockchain. I can track it because ledger is immutable. And how I get immutability, we'll see the technical part. Now there's a notion of consensus algorithm. So consensus algorithm is one such is proof of work. And how proof of work works, let us see. So whenever a new transaction is there, it is broadcasted to all node by flooding. Node collect new transaction to the block. In each round, a random node is selected, and he casts a block out of those transactions, and he floods that block to everyone. And then the blockchain gets appended. So this is the same thing I was telling. So proof of work, how proof of work works actually. So the scenario is this. So what is happening? See, if this is the transacting party, A to B, he is sending 1.5 Bitcoin. So this is the full node. He is having this all transaction which happened in last 1 minute. He is having this in its memory pool. And he is a mining node. What he will do? He will cast a block out of a blockchain. He will cast. So this is a full node. This full node could be, A, it could be B, it could be C, it could be any C. So what I'm talking about, see, A, B, C. These are the three nodes. So one of them have participated, started this, the transacting party could be either A or B or C. Any party has started transaction, he has sent this. Now this transaction, everybody is having this memory pool. A is also having this memory pool. B is also having this memory pool. C is also having this memory pool. Okay. Now they will compete with each other to cast a block out of this blockchain. So what happens? So I have to cast a block. So I can cast a block. I include all these three transactions. I cast a block out of this blockchain. Okay. Whoever cast this block to the blockchain, he is rewarded. He is rewarded in the native currency. He gets some Bitcoin. He gets some money. So all of them will compete with each other, and it's called proof of work. Okay. What they do? Everybody will try to, all transactions they will put, previous block has it, they will try to find a nonce. So they will try to find everybody will try to find a nonce so that the hash value I get on this combined data, the hash function I compute, its value should be less than some target hash. Maybe it should start with 4, this one. So what I'm doing, see what I'm doing. See, I have to cast a block out of a blockchain. So I'm extending this block, or I'm adding this. So this is the blockchain. So I'm casting a block out of this transaction. All transaction I put here. All transaction I put here. It is fixed. Previous block, whatever is there, this hash I put here. Now I compute a hash function on this. Now nonce is the number. Any number used only once. I start with 0 and I see what hash value I get. If hash value I get is 0x123, that is not the hash I want. I want a hash value to start with this many 0. 1, 2, 3, 4, 5, 6, 7, 0. Okay. So at least you have to try 2 to the power 7 times. Okay, 1, 2, 3, 1, 2 to the power 7 times to get a nonce. Different nonce value you have to try, and in this simple example you have to try 2 to the power 7 different nonce, so that one of them will give you the hash value that start with 7, 0. This is called proof of work. This is called mining difficulty. This is called mining. Okay. Whoever finds this nonce first, he will be able to add this latest block into the blockchain, and he will be rewarded. Okay. Anybody wants me to repeat this? Anybody wants me to repeat this? Anybody wants me to repeat this?
Yes, sir. Please repeat. Actually, I am not understanding that nonce concept.
Okay. इसमें अभी रखो ना, बाद में क्लास ले रहे हैं, बाद में लाना. हाँ. So what happens is, like what I'm telling is, see, transacting party has given this and broadcasted this transaction to all nodes. Let us assume that in our example there are only 3 parties, A, B, C, and they have to reach to a consensus. They have to reach to an agreement. Agreement on what? Next block has to be added to blockchain. This blockchain everyone agrees. So A, B, C is having this state of the blockchain. 1, 2, 3. This new block has to be added to the blockchain. So the first problem is, who will be given chance to add this block to the blockchain? Because whoever adds block to the blockchain, he will be rewarded with money. Okay. Now what they do, all of them will compete with each other. And how they compete? They solve a mathematical puzzle. What is that puzzle? So this memory pool, everybody is having. What was the transaction that happened in last 5, 7, 10 minutes? Everybody is having. A gave 1.5 Bitcoin to B, C gave 2 Bitcoin to D, M gave 1.1 Bitcoin to K. Everybody is having. So I cast a set of transaction. Okay, in my new block. I have to find a nonce. I have to find a number, nonce, and previous block hash. I get from this block. This block hash I put it. And I have to run a hash function on top of this. And the hash, the output which I get, it should start with 4, 0. See, in this, transaction is fixed, previous block hash is fixed. What I can change is nonce. I start with 0, I got some hash. No, it is not starting with 4, 0. I change it to 1. Then I see what hash I'm getting. I keep on doing this. 3, 4, 5, 6, 7, 8, 9, 10. And eventually I will get a number, say 1,02,000, 1,02 number gives me a hash that started with 0. So I won. So my block will be added to the blockchain. Whoever finds this nonce first, he will win. This is what I'm telling. So this block I am casting out of the transaction in the memory pool. All transaction I have taken is this. Previous block hash is fixed. I cannot do anything. What I can change is this nonce. I have to find a nonce. Such that if I apply a hash function onto this, I get a hash value that starts with this many number of 0. This is called difficulty. Now I am making sense. This is making sense to you? So this is called proof of work solution. Okay. Now there are 2 types of blockchain. One is called public, another one is called private. So in public blockchain, anybody can participate, anybody can read the content of a blockchain, anybody can add data to the ledger, and it is free. So Bitcoin is an example of public blockchain, and there are no rules or permission around which who can trade, who can buy, who can sell. Anybody can join. All you have to do is you have to download a Bitcoin client, and then you can participate. Private blockchain is like target based. There are nodes where you want this only set of node you want them to exchange data with. Okay, then there are private blockchain. So public blockchain, anybody can participate. Private, it's owned by single organization. It is completely decentralized. Anybody can write. It is partially decentralized because anybody can flood the transaction, but writing on to the transaction onto the blockchain will be done by set of authentic nodes only, authorized node only. They are typically very fast. The number of transactions that are added onto the blockchain is less, maybe 7, 10. And here in private blockchain, it is fast. You can add say 1500 transactions per second. It is also called permissionless because you don't require any permission to add to the blockchain. And it's called permission. Efficiency is low and high, and then we can read it. Now, type of blockchain is public blockchain and private blockchain, and it also permission and so public, private, and again it is repeated. It was public. Oh my God, permission and permissionless. So the slide got repeated. Sorry. So permission and permissionless is that permissionless blockchain is you don't require permission of other to join to a network, to flood a transaction, to write block to a blockchain. You don't require anybody permission. All you require is download that code and become the member of that blockchain. Private is it is permission. Unless until you are authentic, node, you are a cashier, you are a manager, your node won't be added into the blockchain. So benefit of the blockchain is it provides a shared infrastructure between organizations, and there's a single source of truth. Means you don't require one copy to be maintained by all organizations. So there's a one copy, all node will see the all copy, how that copy is changing. Okay, and it is fault tolerant. There's no single point of failure, and nobody can change the content of that blockchain. It is immutable. It is immutable. Immutable. And how it is immutable, we'll see. It is immutable, and nobody can change it. Okay, it removes intermediary. You don't require any intermediate body that will be taking care of this transaction happening between two nodes. Okay. The drawback of the blockchain is blockchain technology is extremely inefficient because it is very new. You will find very less trained person working onto the blockchain. If you start onto Hyperledger, Ethereum, and if you get any error, it is very difficult to debug and work onto that. And the number of transactions that you can have onto the blockchain, say Bitcoin, is very less than what Visa offers you. You cannot directly migrate from blockchain. Bitcoin you cannot directly use for, you are having tea and you want that transaction to happen through Bitcoin. It is not possible because throughput is very less. Number of transactions it can support is very less. And there are vulnerability. It is vulnerable to denial of service attack and 51% attack. So blockchain is decentralized. It is immutable. It is transparent. It is disintermediated. It is consensus based. All these technical jargon. Now we'll see the technical part. How we achieve this? How we achieve this immutability, transparency, and how we achieve this. So the technological innovation in blockchain is, the first thing is hash pointer. Hash pointer is a special type of variable that holds hash of the, typical pointer is a variable that holds the location of a other variable. It's pointed to other variable. Hash pointer holds to a location of a data whose hash value is this. Okay, hash value is this. So what it looks like, it looks like this way. So this data, I put hash of this data, hash of this I put onto here. Okay, hash of this I put onto this. So this is called linked list with a hash pointer. It is called blockchain. So whenever in a pointer you don't hold the memory address of previous node, you hold my previous node. My previous node is a node whose hash value is 0x1234 ... So you see what node hash value is this? What node hash value is this? So this is the node. So this is the node whose hash value is this. So that is my previous node. It is like that. Okay. So what happens, just for our ease, we store the previous node hash here. But if I'm having a long chain in our machine, in my native machine, I can hold location also, address also. Then life becomes easy to navigate. But what happens, the problem comes in hash pointer, I don't store an address because the blockchain on different machine have different address. So my previous node pointer I cannot maintain. Physical 64-bit machine hai, someone is 32-bit machine, you cannot. Only hash pointer is what works. Means it holds the previous node is the node whose hash value is this. That's it. So you have to try, you have to work it out on all node. What hash is this? Yes, here's my previous node. And so just for ease, you can keep the location address also as a supplement. But typically that is not in blockchain definition. Okay. Now what is happening? I have a data, the previous hash. I compute a hash onto this hash function. Whatever is the outcome, I write here. I compute hash onto this. Okay. Whatever is the outcome, I write here. Okay. And then whatever is the, I compute a hash onto this, whatever is the outcome, I write here. Now what happens? This blockchain can be used as a temper evident log. Means if anything you change it, if you change here, then what will happen? This hash won't match. Why? Because now this, if you write a hash of this, then whatever is the output, it is here. It is here. Okay, it won't match. It won't match. Let us take an example. See, let us assume that previous hash is 5. This is 3. Okay, 5 plus 3 is 8. This is 8 and 5. Okay, and this is 32. Now, 5 plus 3 is 8. I write 8 here. 8 plus 5 is 13. I write 13 here and 2. Now, if I change data from okay, if I change somehow the 5 was changed to 6. Okay, let us do the other way around. This is 5. This is 3. This is 8. Okay. But it should be this one. Okay, let us make it 9. And this is 11. 8, 9, 17. And then say 3. Let us take my example. Let's take my example, 20. What happens if I change this 5 data to 3, then what will happen? 3 plus 3 is 6. It is not matching. Then I have to change this to 6. Now, earlier it is 17. Now, 9 plus 6, 15. This is not matching. Then I have to change to 15. Now, 15 plus 3, 18. Now, I have to change this to 18. Now, this temporary event log, you cannot change it. Typically, what happens if hash is what you remember, then nobody will be able to change anything. It is called temporary event log. Because I have to change this, then, so let me show you one demo. This is a blockchain demo, online demo. So hash, if I am writing Rakesh, then this is the hash I am getting. Okay. If I write Rakesh 1, hash changes. Every time if I write ABC, then hash changes to this. So this is a very good site on blockchain demo. If you type onto Google blockchain demo, you will get this sandersbrownword.com. What is block? What is block? So this is the block I was talking about. So this is a 1 and this is a nonce. With this nonce, you start with 40. Now, if I write data 1, now this is not a valid block. Why? I want a valid block hash to start with 40. I'm mining. I'm finding a hash. Yes. If I keep this nonce of 6480, so once you are casting a block out of a transaction memory pool, then here you write all data 1, 2, 3. So this transaction happened. Now this I want to add to a blockchain. Then I have to find a nonce that gives you a hash starting with 40. For example, it could be anything. Mind equality changes 4050. Now this is the nonce 94,232. So now I am able to add block to the blockchain. And how blockchain looks like? It looks like this way. Now this is a blockchain. This is the blockchain. So with block number 1, nonce this, without any data, this is the previous hash 0, and the current hash onto this is this. If I change this, now what is happening? I'm telling you. If I change this, now if I apply hash on this nonce, then I get a hash which starts with 40. If I add 2, now this is invalid. Now, because onto this block, I want a hash to be starting with 40. So this is my hash. Is there any question? Okay. So what is happening? I have to run this. Now, if I change any data anywhere, so for example, no data is here. If I am having this 1, now I have to mine it. This is now okay. Now I have to mine this also. Okay. Why mine this is also? Because now hash has changed to this one. See, previous hash is 0037 this. Okay. I have mined it. I have changed this hash. Now see, what is the previous hash of this? 0005 this. Now it is not matching. It is not matching. It is not matching. It is not matching. Why it is not matching? Because I have changed this 40. Okay. Let us repeat this. What I am telling. See what I am telling. Previous hash is 0. Here previous hash is this 005. So see, this is matching with this. This is matching with this. Previous hash of this is hash of this block. Okay. I've told this is the Genesis block. As of now, it is empty. No data is there. Now, if I want to add data to this, so this, for example, demo purpose. This is 1. If I add 1, now everything, all blockchain is invalid. Why? Because if this is the data 1, okay, the hash is this. Hash is this. Okay, 7614938. Okay, I have to mine. I have to find a nonce that gives me 40. That's starting with this. Now here, the hash should start with 40. It is not starting with 40. 40. No, means something wrong. Someone has changed this one. Then you have to mine it. All hash has to be. So every block, including hash, the nonce should have the hash value of the block should start with 40. Then only block is not tampered. Now I have mined. I found a nonce, correct nonce here. Now I have to mine everywhere a new nonce. 35,230 will change to new nonce. I have to mine everywhere. I have to change every block. This is what I am telling. This is what I am telling here. That if I have to change any data, then I have to change all hash value. All hash value. That is why it is called tamper evident law. It is called tamper evident law. Okay. Now, and how do I store data into this one? It is based on Merkle rule. So all transaction I take, hash of this, and this is the hash of the entire transaction. Okay. Now let us design a digital currency. Now, before designing a digital currency, we'll see how you ensure that your transaction is secure. Now we'll see the transaction. Now, how I design a digital coin? I design a digital coin. So say RBI, he has generated a money, he has printed a money, okay, and its ID is this. And RBI, everybody knows RBI private key he will keep with himself, and public key he will give to everyone. Now, whatever is the coin he has generated, who owns this coin? RBI. And this is signed by RBI, means anybody can verify that RBI has created this coin. Yes, he can create that coin. Now what happens? How transaction is secure? How transactions are secure? See now, as of now, RBI owns this coin. RBI has printed money. He is the owner of that coin. Now RBI can, how I can get a notion of digital coin? That is what we are doing this. So RBI can give this money to his friend. Okay, friend. By once he get a book in his service, say okay, he can give money to any builder. Okay. Nitin Gadkari, road was constructed, he printed that money, he gave that money to, because RBI money, Nitin Gadkari is the government guy, he can take, so he took that money and he has given to the constructor or contractor. Now contractor, this will be signed by whom? Paid to public key of the friend, signed by the owner of this money. Who is the owner of this money? RBI. This signed by RBI. So I am giving this money to my friend, and the money which I am giving, I got from here. And this money is the coin I have created. It is signed by whom? Already I have told you digital signature concept. Signed by RBI. So this is the, so how do you know that this is the authentic money? Because this was created by, it has got a unique sequence number and it is signed by RBI. Khatam. RBI prints note and you have a signature of RBI governor. Likewise, this is digitally created, a unique ID is created and signed by RBI, and this is given to the next guy, his friend. His friend can give this money to his friend Arvind, pay money to Arvind, and friend is signing with his, what? Private key. And anybody can verify with his public key. He is signing with private key. And how do I know that? So this is the traceability, hash pointer. So this money which a friend is giving to Arvind, from where he got that money? I will follow the hash pointer. Oh, he got that money here. Okay. From where friend got this money? Friend got this money from this RBI has signed this. Okay. Yes, RBI has. So this is okay. So this is the way actually you get the protection in a transaction. So here you replace the transaction with your this one. Okay. The problem with this is double spend. What can go wrong is double spending. Double spending is the problem. Okay. What will happen if your friend has given the same money? You can make multiple copy of a digital this one. Am I right? Because you don't have, this is not possible in our real life, because you have 100 rupees note. 100 rupees note, either you give to your friend Arvind or you give your friend to Ravi. You cannot go to give to two fellow. But here, since it is in digital world, you can give the money to two of them. This was the fundamental problem in digital currency design. It was solved in Bitcoin. It was solved in Bitcoin, and how it was solved, we'll see. The major challenge was double spending. And how it was stopped? It was stopped by these concept was combined together, and peer-to-peer network, hashing, private public key cryptography. And what we do is typically we put multiple transactions in this one. Okay. And how do I create a coin? How it is created a coin? So whenever a coin is created, okay, whenever a coin is created, it is created with an ID. So this is the coin. RBI has printed a note, and he has given 3.2 rupees to this recipient, 1.4 to this recipient, and 7.1 to this recipient. Okay, he has created this. Now, what happens, in any transaction, entire this money gets consumed. Entire this money gets consumed, and you get a new participant, and new participant will have new ID. And we'll see the example of this in our transaction system design. Don't worry. Okay. So in every transaction, that money will be consumed, and new money will be created with a new sequence number. That is why there's no repetition. You cannot do that. We'll see how this is done. So let us see one example. Current transaction system. So what we'll do in next 10-15 minutes, we'll design a current transaction system, and then we'll use some cryptographic technique to design a blockchain system which is equivalent of current transaction system. And then we'll see its application. Then application thinking, you can think for your own use case and you can work it out. This is what happened. Whenever consumer A want to transfer 2 Bitcoin to B, then what B does? B maintains. So currently A balance is 2, B balance is 7. Then if A has transferred 2 rupees to Bitcoin, then he will update the balance 0, 9. This is what happens in your banking system. The problem with our banking system is this. What he can do, okay, other don't have accessibility of this. Who is having this ledger? Only bank. He is having the ledger. Now what he can do, he can add a list, and he can give 100 rupees to him out of thin air. Nobody knows. Nobody will be able to verify it. From where Alice got this 100. So in transaction, out of thin air, you can falsify a transaction, because SBI is not doing this, but there is a chance of doing this. What he can do? He can say, Ali can transfer Joy $50, even though Alice don't have $50. So he can falsify transaction. He can say Alice has transferred 50 rupees to Joy. Who will check Alice has that money or not? SBI or any banking system. Okay. He can change the old transaction from 5 to 1. I can change the old transaction from 5 to 1. He can do anything, because so centralized solution, one entity records the data. So lot of power and responsibility we are giving to that this one, and he decides your rule. He say, okay, you take my credit card, I will give you this much bonus. He decides with your money to give loan to different organization, and you get NPA. Okay, in 2008, 7-8, that financial breakdown, because of which this Bitcoin it was brought. So you have this problem of NP. The centralized, he is taking your money, and he could be decideful, and there is a single point of failure. Now, the problem with central authority is I can issue currency out of thin air, I can edit old transaction, I can make new transaction, I can delete anybody's account. They are not doing, but chances are there. And there's one copy of this ledger. So what we can do? So how ledger is made and records are made permanent in any system. So we'll take an example of banking system. So we'll learn how to build a ledger out of this. So there's a very nice slide. Complete slide I have taken from this Professor Sandeep Sukla from IT Kanpur. So how we build a ledger of transaction and how we make it verifiable. So how we build so as of now, your ledger looks like this way. Ram has balance of this, Sham has balance of 300. Okay. Now what happens? I can put a ledger like this way. Debit account, credit account, this is the amount. So initial deposit, Ram has deposited 2,000. And once you open account, initial deposit, Sham has deposited 3,000. Okay. Ram is sending Sham 1,000 rupee, and Sham is sending money Ram to 500. And out of this, I can get this balance table. Okay, how balance table works? You have a 2000 minus 1000 plus 5, 1500 and 2500. Now, in this setup, when we say a transaction is valid, we say transaction is valid if the sender balance is more than the amount it is sending to receiver. Am I right? So, transaction is valid. So, here it is okay. Here it is okay because Ram has sent 1000, already Ram is having 2000 and Sham is sending to Ram, already Sham is having that much money. It is okay. Now, how we can make a ledger out of this transaction? So, whatever transaction happened on 21st September, I put all transaction in one block. And next day on 22nd September, next block, and I can cryptographically link everything. I can do that. You can have anything, land record, whatever registry is happening today, I put all registry in one. Okay. Whatever drug is manufactured in any agency, I can put all batch number here, whatever, and I can get a history. Each block has a transaction of specified time period. Okay. And the blockchain is, they are linked. And how they are linked? You apply a hash function on everything and you put this hash value here. You apply hash on everything, you put hash value here. So you can get a ledger of transaction. You can get a ledger of transaction, but there are drawback with this ledger. What is the drawback? The first thing we did is now a blockchain is a distributed ledger of transaction. We have done this. Now how we get verifiability and permanence? So the first problem is repudiation. What can go wrong? What can go wrong? This can go wrong. What is this? He can say that, let us see where. See, in this transaction, Ram has sent to Syam 1000 rupees. But what will happen if Ram denies? No, I have not sent Syam 1000 rupees. Then how you take care of repudiation? Ram is denying. Ram claims, I never paid Syam 1000 rupees. Then what is the solution? Typically in banking, you put signature in your check. Here what we do, we ask for signature. So Ram, if he is paying 1000 rupees, Ram will use his private key to sign and get a signature. And at the receiver end, along with message and signature, with his public key, it can be verified. So with signature, I can verify. Okay? With signature, I can verify. And nobody else can forge the signature. Given this and given public key of Ram, nobody can. So this is the Ram's public key and 1000. Nobody can change this one and forge. It is not possible. Okay? Nobody else can forge signature without Ram private key. You are getting point what I'm telling? It is not possible to change this 1000 to M dash and find a signature, new signature, sig dash, and with the public key of Ram. You cannot forge it. Okay? So Ram, you cannot forge that. So what we do? Along with deposit, I put digital signature. So what is happening? Whatever is the initial deposit, I put digital signature. So Ram is sending money to Syam. Along with this, I put this is a digital signature on this message. What is the message? Ram to Syam 1000 rupees. This message, I apply hash function. I get a digest. This digest I encrypt with private key of Ram. Okay, I get signature. So this is the signature I'm talking about. This is the signature. Okay, and this is the message. You can compute this message out of these three. With signature, first problem is solved. That non-repudiable register. This is a non-repudiable register. Ram cannot deny that I have not sent. Then how transaction is valid? Any transaction is valid if sender balance is more than the amount being sent by sender receiver and transaction signature is valid. Means sender public key succeeds. Signature is valid. Okay, signature is valid. Now, how do I know what is the public key of Ram? How do I know that what is the public key of Ram? How do I know a public key of Ram? If bank is the one who is managing your public key, private key, then bank can forge your signature because he is knowing your public key, private key both. So what I do is this. We bind account number with public key. You are getting my point? The first problem was Ram should not deny. So Ram should not deny that I have not sent. What I did, I added digital signature. But for digital signature, I need public key. Now public key, if I have opened my account with the bank has created public key, private key, then bank can forge my signature. No, that should not happen. I will decide my public private key, and I will bind my account number. I will bind my account number with my public key. And how this will happen? Whatever is my public key, I do hash, and this becomes my account number. Okay. This is, so customer choose a private or public private key, and he performs a hashing of this public key, and then I get account number. So in my transaction, I have my sender address is the account hash of this. Hash of this is this. Okay, account number. So what I do, so every transaction will look like this way. This is the public key of the sender. I am the person who is sending. This is my public key. Yes, I am telling you. And hash of this is this. Okay. Receiver account address is this. So receiver, whatever public key receiver has chosen, public key receiver has chosen, I perform hash onto that. This is that account address. 1,000 rupee I am transferring, and this is the digital signature. So with this, what is happening? With this transaction, I am telling that this public key, and why I need public key? Because this public key will help me to verify the signature. And this public key hash is this sender. But sender address, this is the account number. This is the account number, sender account number. This is the receiver account number. 1,000 rupee I am transferring, and this is the digital signature. So digital signature is needed for non-repudiation. Here only I am putting this public key so that sender is knowing about his public key, and sender knows about his account number. So with this, I am the owner of my private key. I am the owner of my public key, and this is the sender address. Okay. Why not just use a simple, why you have a sender address here? Why not a public key? Because public key address, they are variable, and you have this, you want this public key so that you can compute this signature very easily. Okay. And then you have a sender address is hash. It's 128-bit. Simple. It is easy to manage your account number. Okay. So one last problem is replay attack. So far what we have done every signature has to be signed by sender. Now who is that sender? I have to bind his identity. What is his identity? His account number with his public key. So how do I choose my account number? I choose my account number as a hash of my public key. And I put every transaction will have public key of sender, account number of sender, account number of receiver, amount I am transferring, and his digital signature. By this, it is, what is happening? By this, it is transaction security. This is the valid, verifiable transaction. Now, what we can go wrong here? If I replay this transaction 2 times, okay, what is happening? Next problem is replay attack. So what happened? The same transaction is repeated again. Same transaction. So 0x111. So this was the beneficiary of 1,000 rupee. Now he did this transaction. He transferred. So he transferred 500 rupee to this account, and this was his signature. So somebody again, if you replace this, then what will happen? Again, I can replay. So he is sending this to 500, and this is the transaction. So after transaction 1, this account number is having at least 1,000. This one. Ram spends some of this by giving to this 500. If I replay this one, what will happen? This transaction, this person will get all $1,000, and his account will have balance 0. But this is not I want. Even if he wants to send money to him, there's a chances of replay attack. Means the same transaction I am repeating again. Okay. In order to solve this, we have used the change address. So what I can do, every transaction, so this is the sender address. From this sender address, 500, this is the receiver and this is the change. Whatever is the balance he is having. So if he is having 5,000 in his account, then 1,000 will go to this account and 4,000 will go to this account, and this account will become 0. Okay. So next time you cannot play the same attack, same transaction you cannot play, because of iske khate mein nothing is there. You have any point? So let's take an example here that if I am replaying this, so what I am doing, he was having 1,000, so he is having 1,000. Let us assume that he is having 1,000. 500 he is giving to him. 500 will go to him. Now again, if I replay this, then what will happen? He is having 0. He cannot send 500 to him and any this one change address. You cannot do because this is 0 now. Okay, this is 0 now. So every transaction, whatever ID you are using, that account has to be 0. In Bitcoin, what happened? That ID was becoming, that coin was completely destroyed. That serial number coin was completely destroyed and new coins were created. Okay. So now the transaction validity comes, and now one more thing, I put a hash of the transaction so that computing digital signature is easy. So for this transaction, everything I put a hash. It's called transaction hash, so that nothing has changed, and just for this one. So now transaction is valid if transaction hash is equals to hash of this, and we verify that signature is valid with this transaction hash. I can quickly verify. This is called record keeping kind of thing. I can verify that transaction is valid. And how do I verify transaction? Because public key is here. So this kind of setting is taking care of all, your transaction is valid. Nobody can change it. If you change this transaction, this won't match. This won't match. Transaction hash won't match. Okay. And he's the sender with this account number, and his public key is this, and you can verify. You can verify that he is the actually owner of this one. Now, how we get this permanent? I get this permanent because this transaction of Ram, Sham, Anil, the same chain of block will be with everyone. So if you change this transaction, then it has to be changed with all other copy, which is not possible because it is our assumption that in our system, majority of them are honest note. This is in our case. Okay. But in Bitcoin, it is done in some other way. Okay. So we were able to design a blockchain banking system, for a banking system where you get permanence. So all participants in the blockchain have a copy of it. So every transaction is broadcast to everyone, and we need a consistent to make sure that everyone sees the same. So whatever transaction is happening, it will be among these 3 nodes. So everybody will see, okay, this is the valid transaction. Then it will be added to a block in a blockchain. Okay. So far, and the last point is this previous hash pointer is important. This is the hash pointer to previous block. It is not the exact pointer. Exact pointer you cannot have actually because different machines, they have different addressing format. Okay. Now these are the healthcare use cases in blockchain. So there are 2. What happened actually? You have Internet of Healthcare thing. Now what is happening? You are putting sensors onto different patient body. They are recording this data. This data is going to your central server. Now central server can run different machine learning algorithm to find a pattern from his food habit, from his BP, from his all different physical parameterity. You can see what is the accurate diagnosis, and you can give suitable treatment. So this is called clinical service. Internet of Health of Thing में all sensors are given to your healthcare organization are using sensor to collect data. It goes to cloud, and then you can use in these 2 settings. One is the clinical setting, means remote patient monitoring, newborn baby you can monitor, and you can give suitable drug what is needed to that patient. Second thing is I can do the tracking and monitoring of the asset. So MRI machine, where is MRI machine? What is utilization of MRI machine? I can do. So healthcare organizations are using this Internet of Health technology to do this proper diagnosis of disease, giving treatment to that disease, suitable treatment, and asset monitoring. Now cloud has got problem. Cloud has problem because it's a single point of failure, data integrity, confidentiality is at stake, cyber attack are possible onto that. So these days, people are working IoT with blockchain. The blockchain gives you certain benefit. And why we need blockchain? First one is, according to US 2014 norm, all health organizations, they have to maintain a digital record of all patients. So electronic health record. Electronic health record is, what is the note of a doctor? Note of a doctor plus all your image, plus all your, this one, lab report. These I digitize and I record somewhere. It's electronic health record keeping is must with all organizations. Okay. And now, so there's a scope for adding blockchain to, because blockchain it's an open software platform, and all participants will see how those participants, whether it is a pharmacy or a healthcare provider, they can share all this ledger. Whatever they are writing, they can write that ledger. Ledger is visible to everyone, and they can decide in a coherent way. So it will ease this business process. Faster medical insurance settlement, we'll see how, and it will help you different party to collaborate with each other, share data in a very secure and efficient manner. Okay. Okay, let us see this. So applying blockchain technology to healthcare is information security. Secure transfer of medical data, it is possible. We'll see the use case, and all the data which a patient will be having all data with himself. He'll be the custodian of all data, and he will decide who can see my data. It's a patient-centric data. And data can be shared among all stakeholders, say insurance, healthcare provider, your patient, doctors, so laboratory organization, clinical record keeping people, researcher. So you give a platform where data can be securely exchanged among all these stakeholders. Okay, so there's a transparency. So you can have a medicine supply chain. Transparency is possible. Processing efficiency is there because all business process become easy. Healthcare, insurance, researcher can directly get data out of this blockchain. All data which is happening, all data which is occurring with the patient. See, all sensor data, it will be recorded onto blockchain and timestamp. So in a timestamp manner, you can see how things are working. These are the company that is using blockchain in their healthcare solution. So what we do? What is the process to design a blockchain? We need blockchain once we have to store a data. Okay, and we need a blockchain if multiple party are writer. Multiple party can write data to a blockchain. Then we need blockchain, and we need blockchain when you have to store a state. So decision goes on to this. Now what happens? Mostly in healthcare organization, we have a permission blockchain. Why permission blockchain? Because in permission blockchain, everybody see data, whatever data is there, not all can participate in data exchange process. Only the person who I recommend, who I permit, he can only participate in this data exchange. Compliance, performance, all security feature I can give in my permission blockchain. In permission blockchain, only the authorized people can write and read data. Okay, and it is more efficient. Permission and blockchain is more fast. It is more cost effective, and it gives you better framework than this one. Now, see blockchain, what happens is like all physician, radiologist, patient, all data, they can be written here. Whatever data is required, we get a single source of truth. Okay, all data from sensors, okay, from patient, it is getting recorded. Lab report, whatever is the lab report, it is getting recorded. He can see all physical parameter of the patient online, and he can make a prescription online, and he can take decision. So everything is blockchain, and people can participate with each other. Researcher can do better research on gene processing, gene dynamics. Laboratory can do this clinical trial, and they can design a drug. Now we'll see the use case. So what is happening in a health organization? He generates that data. That data will be written to. So what is that data? All scan report, all doctor prescription, all lab report will be written to blockchain. Now this blockchain will be available to all party. This all party, new hospital, they can pass query. If he's permitted to see the record, he can see this record, and he can also act accordingly. So sharing of data has become easy. Patient data will be recorded onto the blockchain. Now as of now, what is happening? I go to Ramakrishna Care, all my record will be with these people. If I'm doing this settlement, money and all, then they can keep, and they can keep with themselves. It can be with NIT because I am claiming for reimbursement. But if I have to share that data to some other, then again a new report has to go. I have to take a report. I have to carry my report with my, with our physically we have to take. And we can have all record. It is possible onto the blockchain that whoever I want my data to see, he can only see. It is possible. We'll see that. We'll see patient data management, clinical trial, drug traceability. These things are possible through blockchain. We'll see. So why data security is important? Data security is important because data not only keeps your lab report and images, they keep your name, they keep date of birth, they address in US social security number, payment account information in US. So you keep all these things. So data security is important. And many data breaches have happened, Many data breaches have happened. 25% of the data was exposed, and Apple also it was exposed. So keeping electronic health record in a centralized location has resulted in loss and inappropriate access to personal data owing to data breaches. Okay. So medical record must be decentralized and secure. So these are the record statistics that shows that data, personal data can be compromised. So what we can do? So what happens? There's a patient, there's a doctor. So you do different sitting with doctor, and doctor will prepare your electronic health record. Doctor will prepare your electronic health record. So electronic health record will have doctor's note. Doctor's note will have your images, and it will have your what? Lab reports. Now these lab reports will make your EHR. Now this EHR will be written onto database storage, and its information will be in blockchain, and it could be also, so in 3 places we are writing. So here actually blockchain we cannot write the entire image because then it will be very expensive. See, kya ho raha hai? All transaction, imagine all transaction broadcasted to everyone. So image everything to everyone. So how much memory it will take? It will consume unnecessary lot of network bandwidth. So we only keep here metadata. Information about this transaction. Actual transaction will be stored in this database, or it will be stored in this cloud, and information, metadata information about this transaction will be stored here, and its location, where this transaction is located in the database. It will be stored in blockchain. Okay. Now it is customized user access. Now the patient, he is the owner of this data. It's a patient-centric approach. Patient-centric approach. He is the owner of this data, and he will say who can access my record. So whoever he gives permission to, they can access the record. We'll see one use case. So what is happening? Patient assigns. What is happening? My data will be in the data lake in an encrypted form, and the information of that data will be metadata, will be stored in blockchain. This blockchain. Okay. So I cannot keep all my data in blockchain because of this cost issue, and because everybody has to reach to a consensus. So the same copy will be with all stakeholders. Unnecessary bandwidth will be wasted. So actual data will be stored here, and pointer to this data will be stored here along with metadata of the transaction will be stored in blockchain. So that hash of this transaction will be stored here. So that if you change this transaction here, this hash won't map. So you can't change it. And this will give you suitable window. If any body, say insurance settlement, wants any query to raise, he can raise query here. He can get this one. This will be encrypted, and he can use that data. Let us take a use case example. So current EHR solution is pharmacy, hospital, laboratory, emergency. They have their own database. Okay, and the data is fragmented. So how I can give using blockchain permission? See, we require a external storage. I cannot keep all my EHR onto blockchain. Why? I cannot keep my EHR into blockchain because if I store 1 GB worth of data on Ethereum, it will cost me $138 million. It will cost $138 million of money. Okay, $138 million of money. It is very expensive. So what we do? We require off-chain storage to store HCR record. So what happens? I store in IPFS, interpretive file system. So it's a off-chain storage kind of thing. This way kind of thing. Off-chain storage kind of thing. Okay. So what I do? I store in a off-chain, and the information about the transaction I store in an identified location of EHR is stored in a blockchain. So what we are doing? Actual healthcare record will be stored in it is EHR, electronic health record. EHR will be stored in a IPFS. And the information about the lab report and transaction happened someday, that will be stored in the blockchain. Data in the IPFS will be encrypted, and you have a proper access control method using cryptography you use using blockchain, and you give only the valid authentic user to share your data. So somebody is asking any question or what? So question I will see in the end. Okay, I don't know if someone is asking. Divakar, anybody asking question? So IPFS is
Yes, sir. Please continue. I think no one is here.
Okay.
It's by mistake.
Okay. So IPFS uses content addressing, means like, so there's a storage structure. I give content name. Typically what happens in your HTTP, is I give IP address and file name. I say get index.html page from this IP address. I get from server. Server. In IPFS, I say hash of the content. Hash of the content, I give it to him, and he returns content to me. So here I give hash content, and here I give IP address. This is the difference. Okay. So what happens? Patient health record will be encrypted, stored in IPFS, and wherever it is stored, that location will be recorded in the blockchain and that block will be returned to the blockchain. Later on, if anybody wants to see record, he will scan through all blockchain, find the pointer location information where this is. So in this block, my record is there, my health record is information, metadata is here. Here I will get the location. I go to IPFS location, I get the data, I decrypt it, and I get this data. We'll see this in action. So what happens is this. So if user, patient, physician, lab technician, I generate key. I generate 3 key: private key, public key, and symmetric key. So private key is what I keep in my wallet, in my mobile. So my dashboard is, so I have patient requirement is in my dashboard, mobile dashboard, I should be able to log in and register. I should grant an access permission to others so that they can, my electronic health record, EHR, they can see it, they can read it, they can edit it. And I can view my own EHR. Now other lab technician and physician, what you want out of this app, you want that they should have their mobile dashboard on their mobile. They should be able to register and log in. They can create EHR for the patient. They can access their EHR if they have the permission. And this is what you want, the requirement out of this app. Okay. Now the first process is either a user has to generate 3 keys: private key, public key, and symmetric key. Private key will be stored in my wallet. I'm keeping with myself. Public key is I keep in my public cloud. Anybody can see it. And I have my symmetric key. I encrypt my symmetric key with my private key, and I store onto the cloud. So this is encrypt the symmetric key with my public key. I encrypt my symmetric key with my public key. Okay, and I keep this onto cloud. Now, how do I grant permission to anyone? How do I grant permission to everyone? So private key I'm having with myself. What I do? I fetch my symmetric key. Okay, and I decrypt it. I decrypt with my private key. I get the symmetric key. I encrypt the symmetric key with the public key of physician. The physician with whom I want to share my record. So physician with whom I want to share my record, what I do? This symmetric key I decrypt with my what? Public key, with my private key. Okay, and then that symmetric key I encrypt with the public key of the physician who want to see my record. And this I put it in my database. Okay. Now, how do I store EHR onto IPFS? So physician, so whatever data he is giving, that data will be encrypted with my private key. My private key, I will give it to him. So this will be converted to a PDF, and then that is my step 2. I will give my private key. Now this will be converted to PDF. Now first I retrieve the symmetric key. How do I retrieve the symmetric key? I retrieve the symmetric key with my private key. And then with that symmetric key, I encrypt. With that encrypted symmetric key, and because here what is happening? Whenever I want anybody to share, I decrypt that key. I encrypt the symmetric key with his public key, so that later on he can decrypt this with his private key and use it. So what happens? I will put this record, I will put this with my symmetric key and put it onto IPFS. Okay. So this private key I have given to the physician, or physician can, if it is possible, that physician can give EHR to me. I can write with my private key if you want. Here I am giving the private key to physician. And now what is happening in IPFS? It comes here. It will be written on what is written in the blockchain. It will written onto the content ID. Where is the location in the IPFS? Its identifier of the user, identifier of the user. These two are there and stored onto the blockchain. If I want to find my record, then I have to scan through the blockchain. I will see, oh, this is the identifier of the user, this is the content ID. I go there and I get the message. How? If I'm the patient, I want to see my own EHR, I'm having my own private key with myself. I query to EHR repository. So my ID. So what are the health record with respect to this ID? So it will return the location ID in the IPFS. Then I query IPFS with the CID. CID will give me the encrypted with my symmetric key. Now how do I get symmetric key? He will give the symmetric key. I decrypt with my private key. I get the symmetric key. With the symmetric key I decrypt it. I get the message. So what is happening? With this, there are three keys: private key, public key, symmetric key. Symmetric key I encrypt with my public key. So if anybody, and I put it there, that can be decrypted with only my, private key. So anybody wants to that key, then I will decrypt that key with my private key, and I will encrypt that key with the public key of the physician with whom I want to share this information. And then he can do that. He can do that. So here the takeaway point is, I have a symmetric key. I encrypt with my private key and keep it with my public key and keep it onto a database. If I have to decrypt that symmetric key, then that can be decrypted with my private key. And that key, if I have to share with some other physician, then that symmetric key I encrypt with the public key of that physician. Okay. Then this symmetric, so I'm not releasing my private key. Symmetric key I can change with time. Okay. Now there are option of drug traceability. I can do drug traceability with the what is drug traceability? Counterfeit medicine are the medicine with incorrect ingredients, wrong labeling, and active ingredients are not up to the mark. And why people are doing this drug trafficking? Because it is a very profitable business, and very easily people can get away with that counterfeit drug. 10% of medicine in the world is counterfeit. 30% of the medicine in Asia, Africa, and Latin America is this, and then this many fail. So what we do? These are the motivating factor for counterfeit drug. What we can do is this. See, the supply chain of the pharmaceutical is, we have a raw material, we give to manufacturing party, they do this packaging, they transport the distributor, and they deliver to these three agencies: clinic, pharmacy, hospital, and customer can use it. Now, challenges in the pharmaceutical supply chain is visibility of entire supply chain. So if he is sending money, he is developing a medicine and giving to packaging, hospital won't know what is the batch number he has given to distributor. He never know. Distributor can add counterfeit medicine, fake medicine he can add, because this is not visible to everybody. So visibility of entire supply chain is not to everyone, and traceability of drug manufacturing is not possible, and multiple documents accrue a wrong supply chain. So what can go wrong? So manufacturer, they have manufacturing license, they record raw material, what batch they are producing, they can write onto the blockchain, and it should be visible to everyone. Distributor, whatever they have license, what is the shipment detail, purchase order, they should write everything. Pharmacy should write all detail, everything, and customer should be able to see all the supply chain. Okay. Now what will happen? So all transaction will look like this way. Senders, whoever the sender is sending, so sender could be this sender, manufacturer sending to distributor, distributor sending to pharmacy, pharmacy giving to customer. So what is happening is this. Now customer will scan QR code. Now whenever manufacturer manufactures any medicine, he will add onto the blockchain his hash code and batch number, the medicine batch number and its hash code. Now this batch code, once it is given to distributor, then again the transaction will be written. Okay, this batch, and how it will be written? Sender will be the distributor, and he is giving to pharmacy and encrypted medicine. This medicine information will be encrypted by the manufacturer public key, okay, private key, manufacturer private key, and anybody can see that. So if everybody, all transaction I write onto the blockchain, then what will happen? Customer can see for any drug, he will see, okay, this was the batch which was manufactured here. This batch came to here on this date, okay, and then this is going to all transaction which is happening between them, it will be written here, and since this ledger are transparent, and customer can see whether the drug is actual drug or it is the counterfeit drug. So this is the same thing. So the supply chain visibility I can add, and it can work. We can do clinical trial. Clinical trial means the data source are different, so we get a hospital data, clinical trial people are doing data, then at home you are collecting your data, and these are all, you get app giving you some health status. Somehow if I can have a blockchain where data from all sources can be combined and you get a single analytics, then it is easy. So clinical trial. So insurance I can do, insurance example we'll do. how to ease the settlement between two party. Okay, how to ease settlement between two party without the involvement of a third bank or any this one. How to make this process easy. So we can design an intelligent application for healthcare. How it works is, it starts by collecting all data that you have allowed access to. Okay, and then we can apply machine learning algorithm to find pattern onto this data, so that from your food behavior, your disease can be linked, from your sleep behavior, from BP, because your data has evolved over time and all data I'm having. So I can apply different machine learning algorithm and I can give certain recommendation to you. So the demo which I was telling you is like, you have an insurance company, and insurance company is writing a small contract that will be deployed onto the blockchain. So any doctor and physician, if any patient comes to him, he is doing the treatment, and whatever the money he is charging, that is again directly charged to executed. This smart contract will be executed and money will be withdrawn from this side to this side. How it is done, we'll see the demo. We'll see the demo. We'll see the demo. So what is happening? This is the remix. Let me tell you how to get to this point. So you type onto Google remix, okay? Remix Ethereum. So the remix Ethereum, this is the interface. Is the interface. So onto this interface, what is happening is this. If I have opened these two, it seems. Let me close, leave, close, leave. So what we are trying to do now is, like, we'll try to implement a remix. We are trying to implement a smart contract on remix. So this is the, what is happening is this. On Remix ID, I can write a smart contract. So there are nodes, there are set of nodes, and whenever transaction is happening, everybody will be able to see that transaction. Okay, and only the genuine user will be able to participate in that contract. We'll see what I'm trying to tell. So this is called panel. There are 3 panel, and solitary I'm writing. So what is this? This is simply a ID. Okay,
Sir,
here I can write.
sorry to interrupt. Sir, your slides are not visible.
My slides are not visible. Oh my God. Samriddhi.
Yes, sir.
Do I have time? 5 minutes.
Sir, yes, 10 minutes.
10 minutes, so I can finish. Okay. Okay. So let me see. Now the screens are visible to you?
Yes, sir, it is visible now.
Okay. Now what I'm telling is this. So this is the remix ID. So it's a, you can write your program, smart contract I can write, and I can deploy, either I can deploy in on Ethereum mainnet, or I can deploy on local network. So we'll be deploying our smart contract on local network and see how actually things are happening, like how I can write code onto this. So this is a local machine with 15 node, how smart contract will be deployed, how people will participate, how things can work. You can test your code here. Okay. And this is the file explorer. So first, and this is the main window where code gets executed. And here the terminal, I see the transaction. Okay. So let me write a new file, and let us name that file to be insurance.sol. Once I do insurance.sol, I get this, and here I have to edit a code. So what this code says, let us see what this code says. Can you see the screen?
Yes, sir.
So what we are doing, pragma is a direction to compiler, and we are writing a contract called insurance, and there is something at owner. There is a variable called owner. So who owns that contract? So contract, whoever deploys the contract onto blockchain, he will be the owner. So generally the insurance company who is deploying, he will be the owner. And there's a citizen for whom we are having this insurance. We are having insurance for citizen. So these three are the variable. This is the name of the citizen, and this is the amount that he is insured to. And mapping is just like a hashing function, key value store kind of thing. So if I give address, and then citizen record will be returned. So if I give address, then I get citizen record returned. And this mapping is known by citizen mapping. A variable assigned to this mapping is citizen mapping. And this is, if I give address, then Boolean value will be returned. So a constructor I have, and the owner value assigned, whoever is deploying the smart contract onto the blockchain, he is the owner. So this is the environment variable, msg.sender. Whoever is deploying the smart contract onto the blockchain, there is the environment variable for that, message.sender, and he becomes the owner. So whoever ID is deploying that, he becomes the owner. And this is the modifier. So this is the modifier, which is the condition which is checked before the execution of a function. So this is a function called set doctor. So this modifier only owner means this code will be, so this code will be executed before this. Okay, first will be verified. So who can set doctor? Who can set doctor? Only the insurance company can owner. Whoever has deployed the insurance company can add doctor, and insurance company can set citizen. Here we are setting the citizen. Okay, and doctor mapping. So if doctor is not set, then we are setting it to be true. And here we are setting a citizen. Yes, we are setting a citizen. And here we are using the insurance. We are giving the unique client ID and amount that I want to be deducted. Okay. Then whatever doctor is sending, the amount should be less than the amount that has been requested. Okay. The amount that is insured should be less than the amount that is being requested, and the amount will be deducted from this one, and you get insurance is successful. Okay. So let us see. Let us copy and paste this code and how you run. Let us see. So this is an insurance between insurance company, and so how do I compile? So these are the all plugin and left hand side of the panel. So how do I compile? So these are all compiler possible. So let us compile. So this has been compiled. Okay, and let us. So this is the way. So compiler, there are many compiling options. Compiler, there are many compilers. So I have written this direction to what compiler has to be used to compile this code. It's 4.26 and above. So he has used 4.26. These are the different compiler possible. And Solidity is the language. And so here the environment is JVM. These are the all account. These are all nodes which I was talking about. ABC. I've given you an example. Here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. 15 accounts are there. Okay. Now this is the address. This is the address. Okay. Who is deploying? I am deploying from. So he is now the insurance company. Okay. Insurance company deploy. So he has deployed the this one, and the good thing about Remix ID is whatever are the function, you get a good setter and view. You can retrieve and you can set. So all function, they have this tab. So how do I set citizen? I can set citizen by setting. Yeah. So this is what has happened from this account, from this XDB, this account, I have deployed. Now, who is the owner of this contract? He is the owner of this contract. Now, who will set citizen? He can set citizen. Let's assume Rakesh. Rakesh. I have to give string, comma, what is the input of this function? What is the input of this function? String, comma, amount. And I am insuring myself with 3,000. Okay. So from this account, I am setting citizen data. Now this is successful. And I can see the output. What is the output? I told you that this transaction, I can see. See, let me see how to maximize the screen. Okay. See, this was the transaction output. What I did, I set citizen. So what is actually set citizen means in blockchain, what is written? These things, this was the transaction executed. Transaction hash is this. This is the transaction executed, and output is this is the address. The client which is created. See, this client. What is the output? If I set citizen, then this unique ID, this address unique ID, and what we are doing. So, so whenever I'm creating a client, then I'm doing hash of message sender. Who is the sender? Sender is the now who has deployed the contract? The insurance company. So his address and the timestamp now that is hash is converted to address, typecasting kind of thing, and then this is assigned a unique ID. So this is the customer ID. This is the customer ID. Let us save it somewhere. Let us save it here. At the customer ID, let us save it somewhere. This is the customer ID and keep text. This is the customer ID. This is the customer ID. Okay. Bad now. Yes. Tum rukna aaj bad na aana. So this is the customer ID. Okay. Now who will set doctor? So who will be the doctor? Doctor will be other node. Let us make this 05B this doctor. Let us make this to be doctor. So once this account I'm adding, I copy this account. Again, who will set the doctor? Doctor can be set from insurance company only. So I have set the doctor. Paste. Set doctor. Now I have set the doctor, and the same doctor has been set or not. I can check. Copy. Doctor mapping. Control V paste. So doctor mapping, it will return Boolean. If this doctor has been mapped, output Boolean true. Yes, doctor. So I have set the doctor, and who is the doctor? Doctor is 5B. 5B, very 5B. And who has installed this, contract? DD. DD has the owner. D is the insurance company. Now, citizens mapping. So citizen mapping, if you want to see the citizens record, so let us take the citizens record, copy, and citizens record, paste, Control D. Now citizens mapping, if I see from here, then again I see this. Rakesh. So citizen mapping has been, what is the output? Citizen mapping is the this. Where is citizen mapping? Citizen by default returns true one Rakesh and this. So citizen mapping is this. So I give address, mapping address, and I get this citizen's information. This citizen information I get. And everything I am running from insurance company address. Okay. Now who is the doctor? Doctor is 0x5B I have set. So 0x5B, let us go to 0x5B. Oh, this is the 0x5B doctor. Now doctor can claim for insurance. So doctor has, so I went to doctor, okay, and then if I done the treatment, he has done the treatment, then treatment for this ID, this is the client ID, okay. This client ID I give to this client ID, and the money I am charging is say 2,000, okay. Then I am in the doctor account. See, if I go to this account, what do you call it? Insurance agent account, I use insurance error. I cannot use. I have to use from the doctor's account. It was 05XB. If I do use insurance, so something wrong happened. So you have this 5XB. Who was the doctor? 05XB3D. Oh, 05XB38D. Okay, let us set doctor from this account, then it will be better. 0xDB. 0x583D. So 0x583D. Where is that account? 0x583D. From this account, if I go to this account and let us use insurance for this kind. Let us try again. Copy. You are getting a point what is happening. You have to execute this from this account. Use insurance. So this is the way actually I have used insurance. Insurance cannot be used from this one. It has to be used from doctor's account only. Okay, doctor's account only. If I do this debug, then what has happened? Use insurance में. So string insurance has been successfully executed. Insurance has been successfully executed, and let us see the citizens mapping. Let us see the citizens mapping or this one. Achha, so far you have any doubt? You want to ask anything? So what is happening? See, it's a simple insurance. What is happening is like I can show you this. the output, the money which got detected, we can see that the simple thing I want to tell is this. If I see the citizen mapping, just see the citizen mapping. If I see the citizen mapping, then 1000 is left, because 3000 already he was having. Now he is having 1000. Okay, he is having 1000. Now what I did in this program is I have written one solidity smart contract. So an insurance company will create a citizen, okay, and this citizen, how much amount is insured, he will be setting data, setting doctor, setting citizen data from that account, whatever account you choose, and then the money will be detected from use insurance will be done from doctor's mapping, doctor's ID. Okay, so this is a simple example we did for healthcare. With this I'm stopping. If you have any question, if you want to see the slide, you please let me know, and then I'll be more than happy to answer. Even if you want any research question, you can ask if you have any doubt. See, it depends. The number of restriction, again, like for example, in Bitcoin, cryptocurrency kind of thing, you have the blockchain, block size is fixed. You cannot have arbitrary size block, say 25 megabyte block. If transaction is of say 1 megabyte, so 25 transaction you can put. It is like that way. So transaction size, it depends upon your application. Okay, typically how much you will put your transaction size. And in your use case, in your healthcare and all, typically all data we put onto efficient data store, maybe IPFS or any data repository, maybe cloud, and hash of their data is actually stored onto the blockchain. So in that setting, you can put lot of data into one block. But as such, I am not aware about in practically in healthcare what is the block size people are using. But typically in Bitcoin, the block size 25 megabyte. And within that, you have to use this one. How many times can we change the public? Harjit Singh sir is asking. Actually, see, it's again, it is up to you. How many time you change your see, public key, private key, how many wallet account you want to keep, how many change address you want to keep. See, in a transaction, I have shown you that the money has to go to some other change address. Now you have to create that many change address. If you want your thing to be secure, you keep your 5-6 public private key mapping. This is taken care of by wallet. So if you have Coinbase wallet, or you have any Bitcoin wallet, if you have, then you can have the wallet by default will create n number of 5-10 number of public private key pair for you, and everything will be assigned to you. How frequent you change, it depends upon your usage, your security level you want. For example, how frequent you change your SBI username password. That frequent you have to, because in blockchain everything is tied to your private key, public key pair. So you are known to outside world by your public key. Okay. Anything else? See, actually in Remix, let me show you this this one. There are ways to do this. I skipped that one because I didn't have time. So there's a question like what happens these days. You can write your smart contract in Java. In Remix, it gives you some. In the beginning, you have seen what are the options. Solidity. You can have Java. So these days, it is possible to write your Java. You can write in Java, and so there are different ways to interact with. Let me show you. This is. Can you see the slide? No, it has not been shared. Can you see the slide?
Yes, sir. It is visible.
So what happens actually, this is the actually I have shown you Web3 interface, their JSON interface. You can write JavaScript, Java program, Python program. Through all these things, you can write your contract. You can deploy in your Ethereum virtual machine, and there are n number of options. Okay, Solidity is one way of this one, easy to start with, to understand. I did this. I find it to be easy, but you can do that. And Remix may you get this interface in Remix may, if you see this. So the first interface will tell you all language that it supports. Remix, Ethereum. So right now I have closed. So it should see, it will show you like Solidity, JavaScript. Now it will show you. Okay. So this terminal is to see this one. I should get this interface. So you have this Chrome version of this one, and you have this. So these are all Solidity. You have Sourcify. There are many. You can see there are many languages you can do, and I'm not aware of all these things. So I'm aware of only Solidity. And if you want this MetaMask thing, then here you have this option of using this one. Okay, compile Solidity and Yule, two languages it supports. Okay, now, those are environment. Those are the plugin for Solidity and Yule. These two languages you can this Remix ID supports. Okay, but if you want Java and all, then you can write your this one. There are ways out. MetaMask is there and options are there. So you can Java, Python, JavaScript you can do, and these are the interface with which you can on real-time Ethereum network you can do. You can do on testnet. You can do on mainnet. You can do that. But for the beginner, if you want to learn for PhD work and this one on Remix ID also or Hyperledger also, my student they have implemented their test cases and your result is acceptable. Okay.
Okay, is there any more questions from participants? Okay, sir, so I think there are no more questions. Thank you so much, sir, for your valuable time and excellent session, along with the practical applications. So thank you so much, sir.
Thank you.
And participants, you can join tomorrow on the same link, on the same time, that is 10:30 a.m. So we'll meet tomorrow again. Thank you. Now I'm ending the session.